All right, we're set for our next lesson on dot product actually. A little warm up. This is just something we want to take a look at first. Then we'll get going, but it's going to help us a little bit. It says if the magnitude of vector p, which we see there, is 5 centimeters, then how would you draw vector q so that vector q is a unit vector, but it has to be in the same direction as vector p. So how would you draw it? Well, a unit vector, we talked a little bit about those before. A unit vector was that little, remember vector I and vector j? They were 1, 0, and 0, 1. They were vectors that had magnitudes of 1. They were special because they were horizontal and vertical. So this one isn't going to be horizontal and vertical. It's going to be in the same direction as p, but I want it to be 1 unit long. So if vector p there is 5, I need vector q. It's going to look something like that. And it would have to be 1/5 of the distance, wouldn't it? If vector p is 5 centimeters, I need vector q to be 1 centimeter. So that's how you would technically draw it. What's actually important, what I needed you to notice here, is I could write it like this: vector q is 1/5 vector p. Right? So I'm multiplying it by a fraction. Multiplying by a fraction here is going to scale it down, right? It's multiplying by 1/5 is the same as dividing it by 5. So it's going to make all of the components that much smaller. But if I divide it by 5, that should give me a unit vector, right? Instead of being 5 centimeters long, now it's just 1 centimeter long. So we're going to use that in a minute. Just a quick look again at dot product today. So not a whole lot new. We have to talk about a couple of the properties of the dot product. We're going to do one more proof just because I kind of like it. So we're going to show you another proof at the end. But mostly today it's just a quick recap of dot product and a few of the properties. So here's the quick recap. Remember we had talked about the dot product originally being defined geometrically as the magnitude of a first vector times magnitude of the second vector times cos of the angle in between. That was the angle in between, assuming they were aligned tail to tail. And then we did that big proof, difficult proof, to show that this statement was true, that a dot b could be calculated as a1 b1 plus a2 b2 if we were given Cartesian vectors. And that one turned out to be a little bit more useful for us. So here, if we're going to try and calculate p dot q, the way we did it was we took the first component times the first component of the second vector and added that to the product of those second components. So that would give us a 12 plus 35, so 47. And remember, that wasn't particularly exciting, but nonetheless, that's the calculation. Same thing here. P dot Q, 4 times 12, plus minus 6 times 8. And that would give us 48, and then a minus 48, which gives us 0. And that was the interesting case, right? If we got an answer of 0, that told us that the vectors were actually perpendicular. The first example with 47, I don't know, again, not that exciting, but the 47 technically means that the angle between those two vectors was less than 90. There's one other thing that I want to show you. I'm just going to get this out of the way for a minute. I can't remember when it's going to come up, but it's going to come up for us at some point. A question like this: determine, well, let's make it really simple. Determine two perpendicular vectors. Give that a try for a minute. Can you come up with any two perpendicular vectors? Pause the video if you need to. Just write down any two perpendicular vectors. And if you can come up with an example, can you come up with another example? We'll do it in Cartesian form, right? So we'll do like, come up with a vector A and a vector B. See if you can come up with a couple that'll work. Okay, easiest two answers to pick. That and that. Right, really simple answer. Those were our two unit vectors, I and j. One is running along the x-axis, one's running along the y-axis. They've got to be perpendicular. And you can check it, right? You can check using the dot product. a dot b is equal to 0. So that works out pretty nicely. What if I did this? What if I said, okay, I'm going to tell you what the first vector is. I'm going to make this be 2, 3. Could you come up with a vector b that is perpendicular to vector a? Is it possible to do that? And it is. You can play around with the numbers a little bit. One thing that I hope you'd recognize, one of the values in vector b better be negative, because we're going to do the dot product, right? If both of the numbers in b were positive, then when I do the dot product will be positive also. So I better put a negative in somewhere. Even put it there maybe. Doesn't matter, we can get away with it in either spot. And there is a neat trick. What you can do that always works is if you take these two components and just switch the order and make one of the signs a negative, then the dot product is going to turn out to be 0. Right? That'll always work. Just take the two numbers, flip them around, and change the sign on one of them. Now we get a -6 and a +6. So those two vectors have to be perpendicular. Okay, and that's going to work. Oh, sorry about the noise. Smartboard panicked there a little bit. We're going to get perpendicular vectors that way. So it's a neat little trick. Basically what we're doing there is we're kind of doing a negative reciprocal idea. If you remember back to grade 9 slope, two lines were perpendicular if their slopes were negative reciprocals. That's kind of what I've done, right? I've switched the rise and the run and changed the sign to negative. Okay, let's move on from there. Here's the unit vector idea, kind of like that warm-up we did. Determine a unit vector that's collinear to vector A, which is 3, 4. So remember in that warm-up we did, I had vector P, and I said the magnitude of it was 5, and I wanted a unit vector in the same direction, and the unit vector obviously had to have a magnitude of 1. Well, for this one, we have to do the same thing. We have to scale down the size of the vector. So the size of vector A is important. We can calculate the magnitude, remember, by doing a1 squared plus a2 squared, which is just, oops, not a very good square root, there we go. And I don't know, you might have known that one already, right? That's just a 3, 4, 5 triangle. So magnitude of A is 5, just like the warm-up was. So if I want a unit vector, my unit vector needs to have a magnitude of 1. So if I want to compare my unit vector to vector A had a magnitude of 5. I need my unit vector to divide vector A by 5. Right? I need it to be 5 times smaller. So we just do that 1/5 trick again, just like we did in the previous one. Now I suppose we could do this. Vector U then is 1/5 vector A. Vector A was 3, 4. And so vector U would be 3 over 5, 4 over 5. And if you feel like playing around with fractions a little bit, if you try calculating the magnitude of that, and you do it the same way we just did for magnitude of vector A, you just have to deal with fractions instead. You get a magnitude 1. So it works. This is officially the formula. This is what we just did though. If we want to get a particular unit vector in the same direction as some other vector, then what we do is we do 1 divided by the magnitude of vector A times vector A. And that's what we did here, right? The magnitude of vector A was 5. So we found that magnitude, and then we used that to help scale the particular vector we started with. One thing to keep in mind here, the vector U is in the same direction as vector A. You also could have done this. I could call it, I don't know, vector V, and make it negative vector U. still a unit vector, and still collinear, right? Just in the opposite direction this time. So sometimes we'll ask for 2 unit vectors. This would be a second unit vector. Collinear 2, just in the opposite direction. These are some properties, different properties of the dot product. The first bullet there we did, right? There's P is perpendicular to Q if and only if. Remember we'd shortened that yesterday, right? We'd said if and only if could be written as IFF. So that's the full statement there. P is perpendicular to Q if and only if P dot Q equals 0. And then it worked backwards, right? If the dot product was 0, then you knew that the vectors were perpendicular. Second bullet, it's called the commutative property, right? We've talked about that one before. The idea that the order doesn't matter. So if I go P dot Q or Q dot P, we get the same answer no matter what. That's helpful for us, actually. The next two, well, the next one, I guess, is called the associative property, which maybe you haven't heard of before. That's a multiplication idea, and it's basically saying it doesn't matter where we put our scalar. So K is just a number. You know, I'm still doing the dot product. It doesn't matter if I multiply that scalar by a vector first and then do the dot product, or if I multiply that scalar by the other vector first and then do the dot product, or third option, which is maybe even the better one, do the dot product first and then multiply that answer by the scalar. Okay, they all work, all the same. Next one's the distributive property, and we're used to that from expanding binomials and things, right? If you have something like that, P dot Q plus R, what's happening is we can just expand or distribute that P inside the bracket. And that's what you see here. And then the third one is just written in the reverse order. That's helpful, that we can expand the dot product through. Kind of a neat one here, P dot P is equal to magnitude of P squared. That's something that we'll probably prove at some point. It's not too hard to prove. And the last bullet there makes, I think, a whole lot of sense. If you do the dot product of something with a 0 vector, you're going to get an answer of 0. 0 vector, if you're writing it in Cartesian form, would just be 0, 0. So anything dot product with 0, 0 is going to give you an answer of 0. Okay, little proof, and then the fun proof after that. The little proof is we're going to prove that commutative property. So any of the things that we had just written down on that last slide could be proven. Can we prove this? So can we prove that P dot Q is actually equal to Q dot P? And this is not a hard proof. It's one of those ones where we're just trying to make sure that we're careful in displaying everything that we needed to. So it helps to start like this. Vector P is P1, P2, and vector Q is Q1, Q2. Okay, so we're actually giving some components to it. So if I want to look at P dot Q, the way that that's calculated is you would do P1 times Q1. And remember, those are just numbers, right? P1 was a number in that component spot. Q1 was another number. P2 and Q2 are just numbers. So that's saying P1 times Q1, a number times another number. And this is the commutative property for dot product, right? If I wrote this down over here, 2 times 3, we'd all agree that that's the same as 3 times 2. That's the commutative property for multiplication, right? We know that that's true for multiplication. And now that we've started this calculation, P1 times Q1, those are just numbers again, right? Like 2 times 3. So I'm allowed to do this. Change the order. Same thing here. And I'm going to put a little note in. I'm going to say, since multiplication of numbers is commutative. So I'm not proving that commutative works for numbers. We know that's true. We're trying to prove that this commutative property is true for the dot product. So I'm allowed to assume that part. And actually, as soon as I do that, that's exactly what Q dot P means, isn't it? start with vector q, and then dot product with vector p. So that's done. Not too hard to prove. Okay. I actually want to show you a slightly different way of doing it. Both good ways. Here's another proof. You don't need the let statements anymore though. If I do it from a geometric standpoint, p dot q would be the magnitude of vector p times the magnitude of vector q times cos of the angle in between. And then I can do the same trick, right? The magnitude of vector p and the magnitude of vector q are both just numbers. So I can change those. I can change that order as well because they're just numbers. And then that's equal to q dot p. So two nice proofs, short proofs. A lot of the ones in this unit can be. It's just a case of recognizing what you're allowed to do and what you're not allowed to do. Okay, last one for us. And again, I like this one. The proof's kind of cool, I think, but then I'm a math geek, so I'm supposed to think that's true. You guys can see what you think after that. Some of you may have heard of this before. If you have 3 points on a circle, so I'm going to say that AB is the diameter, okay? It's true that if I put a point C anywhere else on the circumference and then connect A to B and B to C, that's always going to be a right angle, no matter where I put point C. So if point C started to rotate around this way or even all the way down here, no matter where I put it, ACB, that corner, is always a right angle every single time, which is a neat circle property. We don't get to teach you guys much circle property, so I'm taking my chance when I had it. What we want to do is we want to use vectors to prove that ACB is a right angle. So I'm telling you it is. We're going to try and prove it. Okay? And it's not a real easy proof. There's some steps in here that aren't that obvious again, but it works out really nicely when we finish. It also demonstrates a couple of the properties of the dot product, which is what we want. So this will be the first time that we've tried to prove something is right angled. We've proven that things are equal before using vectors. But if we want to prove that, well, if we want to prove that it's a right angle, that's the same as proving that, oops, that's not the way I wanted to write it. We want to prove that vector CA is perpendicular to vector CB, right? Prove that that vector and that vector are actually perpendicular. That's equivalent to proving that the dot product of those two vectors is 0. So that's what we're going to try and do. Can we show that CA dot CB equals 0? So we need to muddle through a little bit with some vector stuff, with the hope that eventually we get a 0 here. We can start it the same way we've done proofs in the past. I'm allowed to replace CA and CB with sums of other vectors. So I'm going to change vector CA into CO plus OA. And then I'm still dot producting that with CB, which I'm going to change into CO plus OB. And why would I do that? Well, two things have happened now. I've got CO twice, which is kind of nice. And I have OA and OB, which are opposite vectors. So that's kind of nice. The next step is using the distributive property. Because remember, properties of the dot product, we said it's distributive. So I am allowed to distribute through the brackets. Now remember, as I do that, we're dot producting all of the answers. So I'm going to slide this over just a little bit so I have more space. So that's going to be CO dot CO plus CO dot OB plus OA dot CO, and then finally OA dot OB. And this is one of those examples where we started with something simple, we've made it much, much bigger in the hopes that then we can simplify it to something else, because we're trying to simplify it all to 0. Okay, I'm going to grab a couple of, I got to do a couple of things to rearrange here. I'm going to leave the CO.co for a minute. You can just stay there. I'm going to pull this one, the OA.OB, and I'm going to write it at the front. Oops. And I'm going to leave the next one, CO.OB. And the only one that I haven't used yet then is this guy. And I'm just going to change the order of it. Right? We just finished proving that it was commutative, so I can write it this way. Not really necessary, but it's going to be a little bit easier to see. Okay, I'm going to keep going. We're leaving the first one again. I'm just going to go in small steps. Leave the next one. But now, this is, I think, the trickiest step. We had distributed earlier, right? We multiplied everything through the brackets. This time I'm going to go the opposite of distributing. The opposite of multiplying through is to factor. I've got a CO and a CO there. So I'm going to factor a CO out of that bracket. Leaves us with OB plus OA. And remember, if things are distributive, then you got to be able to factor them too, right? They're just opposite operations. So that's what we did there. Can you see why that was a good idea? We mentioned it a second ago, right? OB and OA are opposite vectors. Now, I guess I should be careful there. I'm going to label, I'm going to put an R there, an R there, and an R there. Those are all radiuses of the circle. So the OB and OA are definitely opposite directions. They're also equal magnitudes, so they're equal vectors. So that'll give us CO. I still haven't changed those in a minute. I have to. We're going to come to that in just a second. But this one is now CO dot 0 vector. And anything with dot producted with the 0 vector is 0. So it's gone, right? This term at the end is now finished. Which means we just have to deal with these first two. We're going to have to look at this one and look at this one. Remember, we're hoping to get this all equal to 0. So I need everything to disappear eventually. This part is gone. So now what we need to do is we need to actually calculate it using our original dot product definition. So CO dot CO. Let me see if I can put that here for you. There's CO. Right. And then here's another CO. So there's my two vectors. Okay. And I'm dot producting them together. So the way you calculated dot product was the magnitude of CO times the magnitude of CO times the angle in between them. Well, what's the magnitude of CO? How long is it? We know that, right? It's the radius of the circle. We don't know how big the circle is, but we don't care. The magnitude of the first vector is R. Magnitude of the second vector is R. Cos of the angle in between. Well, that means I have to take these two vectors and line them up tail to tail, right? If I line them up tail to tail, whoops. Oh well, let's move this one. If I line them up tail to tail, the angle between the vectors is 0, isn't it? So cos of 0. Okay, then the next one, OA dot OB. There's OA. There's OB. Magnitudes of those are both R as well, aren't they? So plus magnitude of OA is R, magnitude of OB is R, and cos of the angle in between these two. So if I take them and line them up tail to tail, the angle in between them is 180. And now this works out really nice. R times R is R squared, and cos of 0 is 1. And the next one, R times R is R squared again, but cos of 180 is negative 1. So that gives us an R squared, take away R squared, which is 0, which is exactly what we were hoping for in the first place. Could we prove that CA dot CB was actually equal to 0? And that's a vector way of proving it. There are lots of other ways of proving it, actually, by the way. If you tried just playing around with some angles, we could have proven it back in grade 9, just with angle stuff that we knew in grade 9. So it can be done, but way more fun to try and prove it with vectors. All right, that'll wraps up our second day on dot product. So there's lots more calculations that we need to start looking at, which we'll do in the next couple days. But I think we have at least a pretty good understanding now of how the dot product works.